So Kepler's third law of planetary motion. Let's go back early 1600s, and the reason the narrator said how you can derive Kepler's law from Newton's law of gravitation and centripetal force, but Kepler didn't know that. Kepler was around about 70 years before Newton, so it wasn't until the 1680s that Isaac Newton identified his laws of the law of gravitation. People really had no idea. It was a great puzzle on how things moved in the cosmos. But by looking at the data, Kepler saw this relationship: the period squared equals the semi-major axis cubed. And I made a comment in the video. You'll see that P pop in, but that's for people who don't know any better. That's for the unwashed masses that have never been in room 123. So you'll be comfortable with the T. You'll see P periodically, but periodically, I crack myself up. T, we're going to use T, semi-major axis cubed. Let's look at a couple things though. Kepler, I showed you a similar image a few days ago when we started this. Kepler was up about 9 years collecting data on exoplanets. And an exoplanet, again, is a planet that's not in our solar system. Identified, you can read 1,200. About 550 are rocky planets. Now, we're pretty sure life can't exist on a gas planet like Jupiter or Saturn, but the rocky planets could have life. 9 of those are in the habitable zone. You may hear it talked about the Goldilocks zone, not too hot, not too cold. The leading theories on life in other planets is that liquid water is probably a requirement. Water being the universal solvent. Does it have to be? We don't know. But that's the most the strongest theory is that if there's life in other planets, it's got to have liquid water. So just a couple years ago, Kepler was retired. Just in time, TESS, the Transiting Exoplanet Satellite Survey, was launched. Within a few days of being launched, the primary investigators announced first light. So first light for a telescope is the first time you've got light that you can analyze within days. They opened this up just to kind of test the optics, and they're able to do data right away. While Kepler only had one camera, TESS has got 4. So four are going to cover a lot more of the sky a lot quicker. TESS has got a 2-year mission. It's already longer than 2 years, and TESS is looking good. Identified 1785-45 confirmed so far. TESS uses a different system though, and so we're going to talk about determining a planet's mass by the period of a satellite around it. Satellite, when I say satellite, I'm talking a moon, or for a star, I'm talking a planet. So TESS uses something called it's looking for a dip in light, and there's two animations there, and TESS is looking for, as it looks at the star, and if an object moves in front of the star, the light's going to dim just a little bit, and that's one of the things TESS is collecting, is to see if the light decreases. Let's jump in to something else. I set us up a simulation so we can get some practice on this, and so I set this up on the PhET simulation. So I've got a planet and its moon, and I'm gonna put it in orbit, and we're gonna gather some data, and hopefully as the data that runs again. What I told you about PhET simulations, they're very accurate. So if I change anything, it's going to be off. So I got a moon moving around a planet, and you see the velocity vector. And I try to keep it circular so we can do the easiest method first. So semi-major axis from that star, and it's pretty good. It's pretty good. So hopefully it stayed in. Shifted a little bit. So I calculated a little different, but it's going to be all right. We're going to use 380,000 because I already built the slide. It shifted a little bit. So our semi-major axis is 380,000 miles. I'm going to have to write the PhET people a note and ask why they use miles and not kilometers or meters. And the period, is 41. Let's have it go around one more time. The period was 41, and if it comes in different, we're going to use that. Yeah, all right. So period is 41 days. We've got our semi-major axis. Teammates, we can calculate the mass of this planet. And let's take a look at that. So Kepler's third law rearranged, or so this can be called a constant, is what they were saying on the video. 2 pi squared, just the pi is squared, not the 4. So 4 pi squared, big G, mass of one planet, mass of the other planet. If the mass of if you're talking stars, planets, moons, this mass, the mass of the planet, if you're talking about a star, mass of the moon, if you're talking about a planet, isn't going to matter a whole lot. So we can get a pretty good estimate of the mass. I'm going to ask you to copy that down in your book on page 171, because I know that the super second hour and the fighting fifth hour, they're not going to be amused with astronomical units. They want to do the math. And so copy that equation down in your book, and I'm going to give you another problem to work on. So you know, I said 380,000 miles. You know we don't use miles in physics. We're going to convert that to meters. You know we don't use days. We're going to convert that to seconds. I already did that, and you know how to do that. 1,609 meters in a mile. And I already did the conversion. So now you got your conversion. We're going to rearrange our variables. So one of these masses is going to cancel. We're going to multiply both sides by mass, divide both sides by period squared, and that's what we get there. Again, I recommend that you rearrange in variables. First, it's going to open up options to you. And then once you've done that, then you can solve. And teammates, I'd like you to take a shot at this with your calculator. The more practice you get, the more confident you will be, and the stronger you will be. So 4 pi squared, just the pi is squared, big G times the times squared. So watch what you're doing here. What I do this times parentheses 3.54 times 10 to the 6 parentheses squared parentheses. I get that number, then I multiply it by this parentheses this number, parentheses cubed, close parentheses, and you will get 8.87 times 10 to the 24th kilograms. And I'm pretty comfortable with this, and I'll tell you why I'm pretty comfortable with this, because I set the mass of the planet to be 1.5 Earth masses, and the Earth's mass is 5.98 times 10 to the 24th. 1.5 is this, and teammates, That is pretty darn good. Whoa. I think 8.89. This should be an 8.9. So 8.89. Pretty darn good. Pretty darn good. Teammates, this is good stuff. This is really, really good stuff. It's going to help you understand what's going on in the cosmos. Recall, we live in a universe. We know we live in a universe now with tens of billions of galaxies, each of which have tens of billions of stars. And it looks like most, if not all, those stars have got planets. So much to discover. I'm going to put this on Schoology as an assignment, but if you're with me right now, I want you to calculate the mass of a planet that has a moon that orbits the planet in 50 days, so its period is 50 days, and its semi-major axis is 2 times 10 to the 6th meters. I want you to calculate the mass of that planet.